AC generators at coal-fired power stations supply most of the electrical energy needed in our country. True. And then 9.1 says, state the energy conversion that takes place when this generator is in operation. So we know fully well that we have AC generators and DC generators, right? So the way I'm going to answer this question, I'm going to answer the question for an AC generator and then also answer the question for a DC generator. So for an AC generator, the energy conversion is mechanical energy to electrical energy, and the same is true for a DC generator, right? All generators, they convert mechanical energy to electrical energy. Then all motors, they convert electrical energy to mechanical energy, right? And then 9.2 says, state one structural difference between an AC generator and a DC generator. This one is very tricky. For an AC generator, we have slip rings, right? Let me write it down. Slip rings. And then for a DC generator, we have a split ring. And then for AC, like we're saying, we have slip rings, right? So make sure you find a way to differentiate between the two. AC, slip rings, and then DC, split ring. And then 9.3, draw a sketch graph of potential difference versus time for this AC generator. Clearly label the axis and indicate Vmax on the potential difference axis. So what is an AC generator? An AC generator produces alternating current, right? But then what do we mean by alternating current? The current changes direction every half cycle, right? So if you wanna plot a potential versus time graph, then after this half cycle, you have to change the direction, right? So we go down, and then after this half cycle, we change direction again, and then so on and so on. That's what we essentially mean when we say a generator is alternating the current, right? And then on the y-axis, we will have Vmax, and then here we'll have minus Vmax, right? So this is for an AC generator. It produces alternating current. But then, like I said, we're answering for both, right? So for a DC generator, we producing a direct current, right? So after half a cycle, the current must not change the direction, right? The current only changes the direction if we have an AC generator, right? So here, if I just put this axis here and then we sketch it, after this half cycle, right, we're not changing the direction for a DC generator. We still keep in the same direction, so on, and so on. So on the x-axis, we still have the time, and then on the y, we have the potential difference, right, and so on. So that's what you sketch when we want the potential versus time for an AC and for a DC. Now let's do 9.4. So 9.4 stories. They're saying that an electric appliance is rated 2000 watts, right? So we know that we measure power in watts. So as soon as I see 2000 watts, I'm writing P is equals to 2000 watts. And then it goes on to say that we also have another rating, which is 230 volts, right? And then it goes on to say that the appliance is connected to an alternating current power source. Okay, and then what we are asked to do is to calculate the maximum current. So we were looking for I max, right? So here in electric circuits, we know fully well that the power is equals to the voltage multiplied by the current. But then when we're dealing with an AC generator, we have power average being equals to I RMS multiplied by V RMS. in the information that we have the power average and we have the VRMS, right? So with these two, we can find IRMS, and then from IRMS, we can then look for a way to find Imax, right? So let me show you what I'm talking about. So in place of power average, we're substituting 2000, right? And then in place of IRMS, that's what we're looking for. So it remains as it is, right? And then in place of VRMS, we have 230. The conceptual physics problem solving is done now. We're just solving the math, right? We're dividing both sides by 230. So IRMS will be equals to 2000 divided by 230, which is equals to 8.6957 amps, right? So now we have the IRMS. We can go ahead and try find the Imax, right? So what is the relationship between IRMS and Imax? We know fully well that IRMS is equals to Imax divided by the square root of 2, right? So in place of IRMS, we have 8.6957, right? Being equals to Imax divided by the square root of 2. Should be obvious what you're supposed to do now. It should be obvious. So Imax will be equals to, we cross multiplying, right? So we have that multiplied by the square root of 2, which is equals to 12.30 amps. And then 9.5 says, let's find the peak voltage. So we're looking for Vmax for the output of the generator. So what's the relationship between VRMS and Vmax, right? Very similar to IRMS and Imax, right? So we're saying that VRMS will be equals to Vmax divided by the square root of 2. We have VRMS, which is 230. Now we're looking for Vmax, right? So Vmax will be equals to 230 multiplied by the square root of 2. And then if you do that arithmetic, we get in 325.27 volts. A simplified diagram of an electrical machine is shown below. Is this machine a DC motor or a DC generator? This machine that we have here is a DC motor. Why am I saying so? We have a power source, so we're converting electrical energy to mechanical energy, and that's the energy conversion of a DC motor and an AC motor, right? So the answer for 9.1.1 is a DC motor. For the last time, why are we saying it's a DC motor? We're saying that it's a DC motor because we have electrical energy. We have a power source here, and then we're converting that energy to mechanical energy. 9.1.2 says, write down the energy conversion that takes place while this machine is in operation. We just talked about it. Electrical energy to mechanical energy. So 9.1.2, we have electrical energy to mechanical energy. And then 9.1.3 says, write down the name of component A in the diagram. Component A is a split ring because we have a DC generator. If we had an AC, it will be a slip ring, right? The difference between a slip and a split is that a split ring is literally split, right? There is a gap somewhere on a split ring. You can see here that we have a gap here in between, right? So because we have that gap, it's a split ring and not a slip ring. So 9.1.3, we have split ring, right? And not a slip ring. And then 9.1.4 says, in which direction will the coil shown in the diagram above rotate? Choose from clockwise or anti-clockwise. So here we have to go to our hand rules. When we have a generator, we use the right hand rule. When we have a motor, we use the left hand rule. Your index finger will point from the north to the south pole, and then your middle finger, which will be 90 to the index, will point in the direction of the current. So let's look at the current in our diagram. We have the positive terminal here, and then we have a negative terminal here. The current flows from the positive to the terminal, right? So here the current will be flowing in that direction, and here the current will be flowing in that direction. So let's use this part of the rotating coil, right? So your index finger will be pointing in that direction. It will be pointing down, right? And then your thumb, if you imitate those directions, will be pointing up, right? So this part here is going up while this part is going down, right? So we have an anti-clockwise rotation. So the answer to 9.1.4 is anti-clockwise. The mistake most people do is that they always want to use the right hand rule, even if they're given a motor. When you're given a motor, you have to use the left hand rule. Let's move to 9.2. 9.2 says an electrical device is marked 200 watts and 220 volts. And then 9.2.1 says define the term RMS voltage. The RMS voltage of an AC is the DC potential difference which dissipates the same amount of energy as the AC. Now let's move to 9.2.2, which says calculate the resistance of the device. Problem solving 101. We have to write the given information down, right? So we are told that the power that is dissipated by our electric device is 200 watts. And then they go on to tell us that there's some voltage VRMS, which is 220 volts, right? And then we are asked to find the resistance. Which equation relates these three variables? You will realize that that is power is equals to VRMS squared divided by resistance. Now you just cross multiplying and dividing both sides by P. You're gonna get the resistance is equals to VRMS squared divided by P. Now we're just substituting on our equation, right? So we're gonna have 220 squared divided by 200. And then if you put that in your calculator, you're gonna get 242 ohms, right? And we can move to 9.2.3. 9.2.3 is that this device is now connected to a 150 volts AC source. Calculate the energy dissipated by this device in 10 minutes. So again, problem solving 101. Let's write down the information we have before we do any calculation. So we know that we have a V now, which is equals to 150 volts, right? And then we know that this device, it has a resistance of 242 ohms, right? We just calculated it. And then another thing we know, we given the time, obviously, which is 10 minutes, right? So we're gonna multiply by that by 60 so that we can convert it to seconds. What else do we know? Yeah, so I think that is it. So we want the energy, right? We know fully well that power is equals to the rate at which work is done. So if you rearrange here, you're gonna get W, the work done, is equals to power multiplied by delta T. So when the question says calculate the power, the energy that is dissipated by a device, you're looking for W, right? All the time. So we have delta T, and then we have some variables here, and we're looking for the power, right? In 9.2.2, we have already said that the power is equals to V squared divided by R. So our V is now 150, right? We square it and we divide by the resistance, which is 242. So now we have our power and we can substitute it back into this equation to find the energy dissipated in 10 minutes. So we're gonna have the energy dissipated in 10 minutes being equals to the power, right, which is 150 squared divided by 242 multiplied by 10 minutes multiplied by 60. We're converting that to seconds, and then we get the energy dissipated of 55,785,12 joules. A simple sketch of a generator is shown below, and then 9.1 says the north and south poles of the magnet remains unchanged. If the coil is rotated in the direction as shown in the sketch, will the induced current flow in the direction as indicated? Answer yes or no. So basically what they're asking us is asking us to determine the direction of the induced current, right? First of all, let's note how the coil is being rotated. The coil is being rotated anti-clockwise, right? And then here is our north pole and here is our south. So with our index finger, we're going to point from the north to the south. Here we are applying Fleming's right hand rule, right? And then after you do that, you're going to pick one side of the coil. Either you're going to pick AB or you're going to pick CD, right? When you're rotating the coil anti-clockwise, CD is going up, right? And then AB is going down. So with your thumb, you decide which side you are taking. If you take CD, then your thumb must face up and your index finger should go from north to south. Let's take CD. So if you take CD, here you're going to have your thumb pointing up. If your index is going from north to south and your thumb is pointing up, and then you turn your middle finger 90 degrees relative to your index, then your middle finger will be pointing from C to D. Let me just use a better pen there. It will be pointing from C to D, right? So the induced current that is given to us on this sketch, right, is not true. So the answer here should be no. It's very difficult to indicate the right hand rule or the left hand rule when I'm making videos like this, but I'll put some notes on the description so that you can see how it works and see why I'm saying the answer is no. And then let's move to 9.2. 9.2 says, is the output voltage AC or DC? The output voltage will definitely be AC. Now, why do we say that? We say that because of the presence of slip rings and not split rings, right? We're saying that because of the presence of slip rings and carbon brushes, right? So it's AC because we have slip rings. And then let's go to 9.3. 9.3 says, what will happen to the output voltage if the coil is rotated faster? So the output voltage when the coil is rotated faster is going to go up, right? So the answer here would be increase. And then another way you can use if you wanna increase the output voltage is to use magnets that are more powerful, right? Or basically increase the strength of the magnetic field, right? And then now we can go to 9.4. 9.4 says, what is the position of the coil relative to the magnetic field when the output voltage is a maximum? That position would be parallel, right? Because when it's perpendicular, that's when our voltage is 0, and then when it's parallel, the voltage is maximum. And then we can go to 9.5, which I've been waiting for this entire time. We sort of are using electrodynamics and electrocircuits at the same time, right? So here we're told that lights in a household are connected in parallel, as shown in the simplified circuit below. So lights, any other appliances, they work as resistors, right? That's just something I want you to note. So we are told that we have two large bulbs rated 100 watts and 220 volts, and then we have another one, 60 watts, 220 volt, respectively, connected to an AC source of RMS 220 volts. And then the fuse in the circuit can only allow a maximum of 10 amps, right? And then let's ignore the resistance of the conducting wires. 9.5.1. So 9.5.1 says calculate the peak voltage of the source. So what is peak voltage of the source? Peak voltage of the source is V max, right? And then this 220 volts that we have here is our VRMS, right? Root mean square voltage. So we're gonna have VRMS equals to V max divided by square root of 2. So what is our VRMS? Our VRMS is 220, which is equals to V max divided by square root of 2. So our V max will be equals to, we multiply in 220 by the square root of 2. So if you do that, I'm getting 311.13 volts, right? I hope you're getting the same thing. And then for 9.5.2, it says calculate the resistance of the 100 watt light bulb when operating at optimal conditions. So let's go to the 100 watt bulb and look at the information we have so that we can answer our question, right? It's rated 100 watt. So we already know that the power average will be equals to 100 watts. What else do we know? We know that it needs 220 volts, right? Because that's given on the rating. So here we're gonna have VRMS being equals to 220 volts. And now what are we looking for? We're looking for the resistance, right? So what is the resistance? When you're working with electrodynamics, instead of having let's say V equals to I multiplied by R, you instead have V RMS and I RMS, and you're gonna use VRMS and IRMS when you're calculating power too. Right, let me just erase this and we carry on. So now we're gonna have power average equals to VRMS multiplied by resistance squared, right? The only difference is that now we have VRMS instead of just V that we were already using. So now we're gonna have the power average being equals to VRMS squared divided by R, which we're already using in electric circuits, but then instead of VRMS we just had V. So what is the power average? The power average is 100, and then the VRMS is 220, and then we square it and we divide by the resistance. So the resistance will be 220 squared divided by 100. So let me just punch that in my calculator real quick and see what I get. So that is 220 squared divided by 100 is giving me a value of 484 ohms, right? And yeah, I think that's all. We can move to 9.5.2. 9.5.3, 5 marks. So we're bound to do some work here, but is it really? Let's see what happens. So 9.5.3 is saying the 60-watt light bulb is now removed and replaced by an electric ion. Okay. An ion generally consumes more power than a bulb, right? Yeah, and then it goes on to say with a power rating of 2220 watts. Makes sense, it's an ion. We are replacing a bulb. Explain with the aid of a calculation why this is not advisable. Yeah, so now what I'm thinking is this ion has a power rating of 220. So for ion, let's just jot down some information for the ion. For the ion, we have a power of 2200 watts, right? And then the ion will experience a voltage of 220 volts, right? Because it will be parallel to the 100-watt bulb, which is receiving 220 volts, because our power source can only give us 220 volts, right? So we have the power, we have the voltage, we can determine the resistance, right? The resistance, and then we can determine the current. What would the resistance help us with? If we determine the resistance, then we can calculate IT, right? The total current. But then another way of which you can calculate the total current is if we just use the power and the voltage, right? So let's say that the power is equals to VRMS multiplied by IRMS. So our IRMS will be equals to the power, which is 2200 divided by 220, and this will be equals to 10 amps. So on this line here that I'm circling now in yellow, let me just make that more appealing. So on that line there, we're going to have 10 amps, right? But then we also have this line here, which will have its own current. We can actually calculate that current actually, because we know the power there and we know the voltage. So okay, fine. Current of the 60-watt battery will be equals to the power divided by 220. So let me just put that in my calculator real quick and see what we get. Where's my calculator? Okay. So we have 60 divided by 220, which is equals to 0.27. So 0.27. And then the fuse can only allow a current of 10 amps. But now we are requiring a current of 10.27. So what's going to happen? The fuse is going to burn out because the current that is required is greater than that which the fuse will let pass through, right? So it will not be advisable at all to have this electric ion on this circuit of ours. A simplified diagram of an AC generator connected to a 25 ohm resistor is shown below. The coil rotates anti-clockwise. And then 9.1 says, name the component that distinguishes this generator from a AC generator. This is clearly an AC generator, and we are even told so. Why are we saying that it's an AC generator? We're saying that it's an AC generator because it has slip rings. If it was a DC generator, it was going to have split rings and not slip rings. So the component that distinguishes this generator from a DC generator is the presence of slip rings instead of split rings. And then 9.2 says, in which direction will the induced current flow in section XY of the coil? Choose from X to Y or Y to X. Here you have to use the left hand rule, right? With your left hand, you're gonna point using your index finger from the north pole to the south pole, because that's how the field moves. And then if you do that, your middle finger will be pointing from Y to X, right? And that's the direction of the induced current. So our answer for 9.2 would thus be Y to X. The diagram below shows the output voltage of the generator for 1 cycle of rotation of the coil. And then there we have it. We have the voltage on the y-axis and the time on the x-axis. And then 9.3 says define the term RMS potential difference. We know fully well that's the AC potential difference which dissipates the same amount of energy as an equivalent DC potential difference. The AC potential difference which dissipates the same amount of energy as an equivalent DC potential difference. And then for 9.4 it says calculate the RMS current of the circuit. So we know fully well that IRMS is equals to VRMS divided by R. R being the resistance, right? So we are given the resistance. It is said to be 25 ohms, but we don't have VRMS. So now what we actually need to do is calculate VRMS first, and then we can determine IRMS. So what is the equation for VRMS? VRMS is equals to Vmax divided by square root of 2. So what is Vmax? We get Vmax from our graph, right? It is 100. Here it is here, where our graph is peaking, right? The amplitude of our graph basically. So we're gonna have VRMS being equals to 100 divided by square root of 2, and then that will be some number. So now we can substitute this value on our equation of IRMS, right? So we're gonna have IRMS equals to 10 divided by the square root of 2 divided by R, which is the resistance, right? And it's said to be 25 ohms. So IRMS will be equals to 2.83 amps, and that's how you would calculate it. And now we have 9.5, which says calculate the average power dissipated in the 25 ohm resistor. The way you would calculate this power is very close to how you calculate power in electric circuits. We know that in electric circuits we have the power being equals to I squared multiplied by the R, or the power being equals to the voltage squared divided by the resistance. The only difference in electrodynamics is that instead of the current just being the current, we use IRMS, and instead of the voltage just being the voltage, we use VRMS. So if we go ahead and do that, we're gonna have power average being equals to let's use IRMS, which we just calculated, right? Being equals to IRMS squared multiplied by the resistance. So our IRMS is 2.83, and then we square it and multiply by 25. That would give you a value of 200.22 watts or joules per second, and then you'll be done with that question. And then now let's move ahead to 9.6. 9.6 says the speed of rotation of the coil in the generator is now doubled. Copy the set of x's below in your answer book and sketch the graph of output voltage versus time for 0.1 seconds, right? So okay, let's do it like this. So we're saying that we know that F is equals to the speed multiplied by the wavelength, right? Let's see what happens if the speed is doubled because that's what we are told here, that the speed of the rotation is double. If you double the speed of rotation, you get F equals to 2 multiplied by the speed divided by wavelength. So basically you multiply the frequency by 2. When you multiply the frequency by 2, we know that F is equals to 1 divided by the period. So when you multiply the frequency by 2, you're basically reducing the period by half, right? So here in our graph, because the frequency and the period are inversely proportional to each other. So if frequency goes up 100% and then the period will go down 50%. Here in our first case here, it took 0.1 second to complete 1 cycle, right? So now because we are multiplying the frequency by 2 or reducing the period by half, is gonna take 0.1 divided by 2, which is 0.05 seconds to complete a cycle. So let me just draw the new graph on this same set of axes so that you can see what I'm talking about. So here from 0 to 0.05, it was half a cycle, right? But now we need a complete cycle because we have increased the speed of the rotation by 2. So it will be something like this. Now we have 1 complete cycle, and then now we need another cycle from 0.05 to 0.1, right? Because in our new graph, it takes us 0.05 seconds to complete a cycle. So we're gonna have something like this. Right, and there we have it. We have our cycle. So the question now becomes, what happens if you increase the rotation by 2.5 times? You know, what happens if you increase the rotation by 3 times?